When Hitler's private diaries were discovered in 1983, the world gasped at the intimate glimpse into the mind of history's ultimate villain. Stern magazine paid 9 million Deutsche Marks for the 62 volumes, which were authenticated by historians who marveled at the signature and the Gothic script. Yet, within days, forensic chemists tore the discovery apart using nothing more than a blue light and a specialized solvent. Those diaries were not written in the 1940s. Because the paper contained optical brighteners and the ink held a compound called polyethylene glycol, neither of which existed until years after the war ended. Each drop of ink and every fiber of paper is a chronological fingerprint. To the naked eye, a 17th century masterpiece and a modern imitation look identical. But to a mass spectrometer, they are separated by the distinct chemical markers of the Industrial Revolution and the Atomic Age. Every material used by human hands has a specific expiration date on its credibility. Forgers spend decades mastering the brushstrokes of the masters, yet they are almost always defeated by the silent testimony of atoms that shouldn't be there. This is the struggle between the art of the lie and the physics of the truth. The most fundamental tool in the forensic arsenal is the concept of the terminus post quem, or the point after which an object must have been created based on its ingredients. Before the 1850s, artists relied on a limited palette of mineral and organic pigments like lapis lazuli, ochre, and lead tin yellow. If a painting attributed to Johannes Vermeer contains even a trace of titanium white, it is a guaranteed fake, because titanium dioxide wasn't commercially available as a pigment until 1921. This was the undoing of Han van Meegeren, perhaps the most successful art forger in history. He didn't just paint like Vermeer. He used period-accurate canvases and hand-ground his pigments. However, to make his fresh oil paint hard and brittle enough to pass for 300 years old, he mixed his colors with a synthetic resin called phenol formaldehyde, better known as bakelite. He baked his canvases in a makeshift oven to simulate centuries of drying. When chemists later dissolved a tiny fragment of his work, they found traces of this modern plastic woven into the 17th century seam. Van Meegeren had successfully fooled the eyes of every major art critic, but he couldn't hide the modern polymers that fixed his lies in place. Paper provides an even more precise timeline than paint. Until the mid-19th century, paper was made primarily from rags, cotton, and linen fibers. It was durable, pH neutral, and lacked the impurities of wood. When the demand for paper exploded, manufacturers turned to wood pulp, which contains lignin, a natural polymer that gives trees their strength. Lignin is the reason old newspapers turn yellow and brittle. It produces acid as it breaks down. If a document supposedly written by George Washington is found on wood pulp paper, it is a physical impossibility. Furthermore, the introduction of chemical bleaches changed the atomic makeup of the page. In the mid-20th century, manufacturers began adding stillbeam derivatives, or optical brightening agents, which absorb ultraviolet light and re-emit it as blue light. This makes the paper look whiter than white. Under a UV lamp, a genuine 18th century manuscript remains dull and dark, while a modern forgery will glow with an eerie fluorescent blue. This simple interaction with photons exposes decades of careful aging work in a fraction of a second. Then there is the definitive mark of the modern era, the atomic bomb. Between 1945 and 1963, atmospheric nuclear testing nearly doubled the amount of carbon-14 in the Earth's atmosphere. Every living thing that consumed CO2 during this period, from the flax plants used for canvas to the linseed oil used in paint, absorbed this bomb pulse of radioactive carbon. While standard radiocarbon dating can tell you if an object is 500 or 1,000 years old with a margin of error of a few decades, bomb pulse dating can narrow a date down to a specific year. If a painting is supposed to be from the 1930s but shows an elevated level of carbon-14, it was undeniably painted after the Trinity test in 1945. This radioactive signature is inescapable. Even the lead used in white paint carries a story. Lead-210 is a radioactive isotope naturally found in lead ore, but it has a short half-life of 22 years. Once lead is smelted and turned into pigment, the lead-210 begins to vanish. By measuring the ratio of lead-210 to radium-226, scientists can determine if the lead was recently mined or if it has been sitting on a canvas for 3 centuries. A forger can steal old lead pipes to make their own paint. But the process of smelting creates a new chemical start button that is nearly impossible to reset. The complexity of ink chemistry adds a further layer of difficulty for the forger. Medieval and Renaissance documents used iron gall ink, a mixture of iron salts and tannins from vegetable sources like oak galls. This ink doesn't just sit on the surface. It chemically bonds with the paper, slowly eating into it over centuries in a process called ink burn. Modern ballpoint pens and printers use synthetic dyes like phthalocyanine blue or methyl violet, which were developed in the late 19th and early 20th centuries. Beyond the dyes, the solvents used to keep ink liquid in the pen provide a countdown. When ink is applied to paper, the solvents begin to evaporate. By using gas chromatography, a technician can measure the concentration of residual solvents. If a document signed by Abraham Lincoln still has high levels of 2-phenoxyethanol, it was signed in the last 20 years, not the 1860s. The solvent levels act as a chemical clock that starts ticking the moment the pen hits the page. Forgeries of ancient artifacts often fall victim to the science of trace elements. Take the case of the Getty Kouros, a marble statue purchased for nearly $10 million. Geologists analyzed the dolomite marble and found it came from the ancient quarries on the island of Thasos. On the surface, it seemed authentic. However, the statue's surface was covered in a layer of de-dolomitization, a natural weathering process where magnesium is leached out of the stone over thousands of years. The forger had managed to replicate this by treating the statue with a mixture of potato starch and chemicals to simulate a millennia of decay. The deception was only uncovered when scientists noticed that the weathering pattern was uniform across the entire statue. In nature, weathering is uneven, influenced by how a statue was buried or exposed to the elements. The forger had been too perfect, creating a chemical homogeneity that nature never produces. Ancient gold coins are often sniffed out by their fingerprint elements. Ancient gold was rarely pure. It contained erratic amounts of silver, copper, and platinum group elements. Modern refined gold is too clean, even if a forger tries to add impurities back in. They rarely match the specific isotopic ratios of the mines used by the Romans or the Greeks. Textiles offer their own unique challenges to the deceiver. The Shroud of Turin remains the most studied textile in human history. In 1988, 3 independent laboratories performed radiocarbon dating on fragments of the cloth. The results placed the flax's growth between 1260 and 1390 AD, coinciding perfectly with the first recorded appearance of the shroud in France. While some argue the samples were contaminated by bacteria or smoke from a 16th century fire, the labs used rigorous cleaning processes, including acid-base acid washes, to strip away modern carbon. The chemistry of the fibers themselves revealed that the image was not painted. There are no pigments, binders, or brushstrokes. Instead, the image appears to be a result of the oxidation and dehydration of the topmost layer of the linen fibers, a process that usually takes centuries of aging or an intense burst of energy. The shroud lives in the tension between archaeological chemistry and theological mystery. But the carbon-14 remains the most stubborn witness against its ancient origin. Modern forgers have tried to fight back by using antique materials. They buy cheap 17th century portraits and scrape the paint off to get a period-correct canvas and ground layer. They find old books and use the blank end pages for their fake letters. But even this has a flaw. When you disturb an old surface, you break the crack allure, the network of tiny cracks that forms as paint and varnish age and lose flexibility. When a forger paints over an old, crackled surface, the new paint seeps into the old cracks, creating islands of new material that are visible under X-ray fluorescence. High-energy X-rays can penetrate the top layers of paint, causing the atoms beneath to emit their own characteristic light. This allows researchers to see the ghosts of previous paintings or the chemical mapping of the elements. If an artist supposedly used vermilion, mercury sulfide, but the X-ray shows the distinctive peak of cadmium, the lie is exposed. Modern scanning techniques can even reveal the individual brush hairs trapped in the paint, identifying whether they came from a modern synthetic brush or an animal hairbrush consistent with the period. Criminologists also look for modern sneaks in the form of isotopes from groundwater. Every region has a specific ratio of oxygen and hydrogen isotopes in its water, which gets absorbed into the wood of a violin or the fibers of a tapestry. If a Stradivarius violin is claimed to have been made in Cremona, Italy, the wood must reflect the isotopic signature of the rainfall in the Alps during the late 17th century. Scientists can analyze the tree rings not just for their width through dendrochronology, but for their chemical composition. If the wood grew in the Pacific Northwest of the United States in the 1990s, the oxygen isotopes will scream the truth, no matter how many coats of antique varnish are applied. This level of analysis makes the world very small for a forger. They must not only match the style, the tools, and the pigments, but the very environment in which the original was created. Ultimately, the history of forgery is a history of the advancement of analytical chemistry. Every time a forger figures out how to fake a patina or a pigment, a scientist finds a new way to look at a subatomic level. The transition from the connoisseur's eye to the spectrometer's data has fundamentally changed how we value history. We no longer have to rely on the subjective opinion of an expert who might be swayed by a beautiful story or a massive commission. The atoms don't care about the story. They don't have a bias. They simply exist as a record of when they were formed and where they have been. The secret chemistry of forgery is the attempt to freeze time. But physics ensures that time always leaves a mark. Whether it is the radioactive pulse of a nuclear bomb or the specific decay of a lead isotope, the truth is written in the elements themselves, waiting for a lens powerful enough to read it. Our past is protected not by guards in museums, but by the immutable laws of the periodic table, ensuring that the real artifacts of human achievement remain distinct from the clever shadows cast by those who seek to profit from the lie. For anyone interested in the intersection of art and science, the lesson is clear. Look closer. The next time you stand before an ancient artifact, remember that its most important features are the ones you cannot see. Its authenticity is held together by a web of chemical bonds that link it to a specific moment in the human story. To understand the science of detection is to appreciate the true value of the original. Support the institutions that use this technology to preserve our collective heritage. And always ask what the atoms have to say about the things we hold most dear. History is a conversation between us and the materials we leave behind. And thanks to chemistry, we are finally learning how to listen to the whisper of the elements.